Okay, we are going to begin now. Can you hear me nice and clear? Just give me a thumbs up if you can. Okay, good. So we have been working on transformation of function, if you remember, and we are going to continue with that even today. Okay, we work on reflection or the reflection about the axis, I should say, reflection about x-axis, reflection about y-axis. We did that. We also talk about the horizontal shift, vertical shift, and in the previous class, we talk about horizontal stretch or compression. Now, today, we are going to talk about, in last class, we talked about vertical stretch and compression, and today we are going to talk about horizontal stretch and compression. So if you remember from previous class, if there is a function f of x, okay, if there is a function f of x, and to this function, if we multiply by a constant to get a new function, then this factor a will produce the vertical compression or vertical stretch. If the value of a is more than 1, if you remember, the graph will be taller, meaning of that is there will be a vertical stretch. And if this value of a is between 0 and 1, then the graph will compress. But the way it compresses, it will be shorter, right? Vertical compression. That's what we did last time. So here what we did is we multiply the entire function, okay? We multiply the entire function value, f of x is the function value or y value by a. So when we multiply the function value by a, the function value will increase. That means there will be vertical stretch. Or if we multiply by this number, which is between 0 and a, the value will decrease, and that is vertical compression. That's what we studied last time. Now, today, we are looking at the horizontal stretch and horizontal compression. So this is a little bit different from the previous one. This is for the horizontal stretch and horizontal compression. So here, the idea is a little bit different. See, if we have a function f of x, okay, if we have a function f of x, and if we multiply this x, look at the screen, if we multiply this function inside the parenthesis by a constant, okay, here is the function f of x. If we multiply the quantity inside the parenthesis, or if we multiply this x by b to get a new function, then this b produces horizontal stretch or compression. So that b produces horizontal stretch or compression. Okay, it will produce horizontal stretch or compression. So now we look at the value of b. If this b is more than 1, when I say more than 1, it's like 2, 3, 4, and so on. If the value of b is more than 1, in that case, there will be compression. If b is greater than 1, then the graph will be compressed by the factor 1 over b, the first bullet point here. Or you can also look at the graph here. See, our function, the main function here is y equal to x squared. That is the function, okay? And if I multiply this by x, in place of x, if I do 2x, you can see it is multiplied by a number 2, which is greater than 1, as you can see. And what we see is the graph gets closer to y-axis. That means the graph gets compressed there. When we multiply by 2, the graph gets compressed, okay? There is a horizontal compression. So there is compression when the value of b is greater than 1. And we say that the graph is compressed by the factor 1 over b. Whenever we say how much it is compressed, we use the reciprocal value. So we say the graph is compressed by the factor 1 over b. But if the value of this one, if the value of b is between 0 and 1, when I say between 0 and 1, the value is like 0.1, 0.2, 0.3, 0.4, numbers like that. Then what happens is the second point there, if b is between 0 and 1, the graph will be stretched by the factor of 1 over b. The graph will be wider. So let me show you there. See, here is our original graph, x squared. If I multiply this x by a decimal number, 0.5 here, you can see the graph becomes wider. It is going away on that side. Meaning of that is the graph is stretched, right? Stretched horizontally. If we multiply by a number more than 1, the graph will compress. And if we multiply by a number between 0 and 1, the graph will be wider, or the graph gets stretched. Okay. And if the value of b is negative, then it will be the combination of those two. And also it will be the reflection about x-axis. So that is the fundamental idea about the horizontal stretch and compression on the graph of a function. So please write everything that you see in this screen. Also try to sketch some of these graphs so that you understand the fundamental concept. So I'm going to give you additional 1 minute or so to complete the writing. And in the meantime, if you have any questions, you can ask me. You can unmute yourself and ask questions, or you can also send your question through chat. Let me check with Diksha. Are we done copying it? Yes. Okay, good. Let me check one more. Let's see. Let me check with Aditi. Aditi, are we done copying it? Okay, then. Okay. So let's move on to example now. How we can use the idea of horizontal stretch and compression to analyze some of the graph of the functions. Okay, let's see. Somehow my screen is not working. So just give me 1 second. Let me stop sharing and reshare it again. Something is not working. Sorry about that. Maybe I need to reload my program here and then share the screen again. Let's see. It is not cold, but it's still frozen, right? Okay, let's see. Can you see it now? Okay. So here is our first example. You can see there are a lot of words there. So I'll give you like 2 minutes to copy this question. Also sketch that graph so that when we perform the transformation, you understand exactly what is going on there. Okay, quick check in here. Let's see. Chandana, are we done copying it? Okay, Chandana said yes. Let me check with Karina. Karina, are we done copying it? Yes. One more. Sagar, are we done copying it? Sagar, no? Okay, let's wait a little bit here. Okay, let's work on it now. So first, let's read through the problem, try to understand what is going on here, and we're going to solve it. Suppose the scientist is comparing a population of a fruit flies to a population that progresses through its life, through its lifespan as fast as, twice as fast as the original population. So there is the key word there. I don't know whether you have noticed or not. The new population progresses through its lifespan twice as fast as the original population, that part over there. Right? There is a key there. The meaning of that is the growth rate is twice as fast. That means if the original population, right, has a certain number of value at a given time, the same value will be attained by the new population in half of its time. Does that make sense? So what they are trying to say is this. So if, and in the question they have said that the new population is R. So R of T, the new population will have the same value as the original population in half its time. Okay. Also, they have explained there, if you cannot get the, factor from this sentence, they have also some explanation here. You can see, in other words, this new population R, this one here, R of T, which is not here in the graph, will progress in 1 hour the same amount as the original population does in 2 hours. So this one will do in half the time of the previous one. Okay, you can see the new population will progress in 1 hour, that is R of T will do in 1 hour the same amount as the original population in 2 hours. Original population in 2 hours. Okay, so if the original population takes half T, then this will take a T. So that is the meaning of that. Similarly, they are given one more hint. It will progress as much as the original population in 4 hours. 2 hours and 4 hours are the same. Okay, 1 hour and 2 hours are the same. 1 hour and 2 hours has the relation. Similarly, 2 hours and 4 hours have the relation. But we know that this new population R of T is faster. Okay, that means it will take half of the previous time. So what we're asked to do is, in this case, we are asked to graph of this new function R of T. So now, let's begin the graph. And when we graph this, we really need to be very careful. See, 0, if we look at this time 0, half of 0 will also be 0. That means for the new population and this original population, the value will be same as 0. The value will be same as 0. So I can put that point. But now look here. At 3, at T equal to 3, the population is also 3. You can see here. 3 at 3. Okay. But the new population will be 3, not at 3, not time 3. Half of 3 or 1.5. It will be 3 at 1.5. Here is 1.5. So when the time is 1.5, it will be 3 up here. So you have to put that point there. like that. Okay, so that means the graph is increasing like this. And then you can see once we look at this 3, now it's decreasing along a straight line. And this value becomes, we look at this value now, this value is a 2. Okay, original population has a value of 2 when t is equal to 6. But the next one is faster, so it will be half as fast. So half of 6 is a 3. That means when t equal to 3, it will be 2. So 3 is here. When it is 3, it will be 2. 2 is there. So we put that point there. So it is decreasing along a straight line. You can see from here to here, it's going along a straight line. So same thing happens here as well. Okay. And then finally, let's look at this one. Here at 7, when t equal to 7, the line has come down to 0, or the population has decreased to 0. Meaning of that is this new population will do the same thing, okay, twice as fast. That means the time, it will not take 7 as the time. It will take half of 7. That will be 3.5. So 3.5 is here, okay, between 3 and 4. So it will come down there twice as fast, like that. So you can put those arrows. So that new graph that we have created is the graph of the function r of t. And now you can see here, if you look at the equation that I have written here, here we are multiplying by 1 over 2. Right here we are multiplying by 1 over 2. Because we are talking about the sense that the time is faster, but the actual way of writing that equation is this one, r of t, because the things are happening faster, right? The things are happening faster. So we write r of t equal to p 2t. This will be the actual equation. This will be the actual equation. Why? Because when we use the concept of faster and when we reduce those time values by half, this value must be 2. The reason is if we are multiplying by a number greater than 1, so this is your b, b is equal to 2, b is equal to 2, and this value is greater than 1. Greater than 1. And you know that if we multiply by a number greater than 1, there will be compression. And if you look at the graph here, the graph gets compressed. Okay, that's why the true equation should be r of t equal to p of 2t. If you are asked to write the equation. In this problem, you are not asked to write the equation, but if you are asked to write the equation, this is how you'll write. Okay, it is r of t equal to p 2t, because you can see the new population progresses twice as fast. Right up there, you can see twice as fast. Twice means 2 times. 2 times. Okay, that's why what I've written here is r of t equal to p of 2t. Why I am emphasizing on this equation? Because later on, you also need to write the equation. But for this problem, we are not asked to write the equation. For this equation, we are just asked to graph. Okay, but later on, when you're asked to write the equation, you must be able to see that. If we multiply by a number more than 1, then there will be compression. Okay, if we multiply by a number between 0 and 1, there will be stretch or expansion. So remember that from the previous slide. When b is greater than 1, then there will be compression. You can see when we multiply by a number 2 here, the graph gets compressed. And when you multiply by a decimal value, value between 0 and 1, the graph becomes wider. So always remember that transformation whenever you are solving even the word problem like this, or when the equation is given and you're asked to draw a new equation. Okay, any question on this one? If you have a question, you can unmute yourself and ask me, or you can also send questions through chat. I'm going to pause here for a little bit just to see if there are any questions. Okay, look like there is no question on this. So I hope you are done sketching the graph. Let me check with Diksha. Diksha, are we done sketching the graph? Yes, okay. Let's go here. Please copy this question now. Sagar, are you done copying it? Yes, okay. Let me check one more. Karina, are we done copying this? Yes, okay. Let's solve this one. So a function f of x is given below. The function that is given here is f of x. We are asked to create a table for the function g of x, which is f of x over 2. Half x means x over 2. So here what they have given is g of x equal to f of half x. So you should know the meaning of this. See, g of x equal to f of half x. When we say half x, this number is between 0 and 1. Okay, this number half is between 0 and 1. This is between 0 and 1, right? Because half is 0.5, or you can say that is 0.5. So that is between 0 and 1. So because this is a number, this half is a number between 0 and 1, we know the transformation. We know what type of transformation is this. So is this horizontal compression or horizontal stretch? What is it, Chandana? Please unmute yourself.
Horizontal stretch.
This is horizontal stretch. Very good. This is horizontal stretch. Okay. We are doing horizontal stretch by a factor of half. Okay. By a factor of 1 over 2 means horizontal stretch by a factor of 2. Horizontal stretch by a factor of 2. So the reason I'm saying by a factor of 2 is because the factor is always 1 over b. If you remember from the original slide, we say that it is stretched by 1 over b, right? We talk about the reciprocal. So that's why when there is a half, the reciprocal of half is a 2. So we say that there is a horizontal stretch by a factor of 2. That means the graph will be wider. Okay, the graph will be wider And when the graph gets wider, the X values will increase, right? X values will increase by a factor of 2. That is the meaning of that, okay? So the meaning of that is, let's write the meaning. So this means the X values gets twice as large for same Y values. Okay, when the Y values remain the same, the X values increase by 2 times. So if we go back to the original graph here, if we look here, you can see somewhere here, let's take this point. See, let's look at that point. On the original graph, right, the value of the function is 4. Look at it very carefully. The value of the function is 4, right? In this original graph, the value of the function is 4 at x equal to 2. This is x equal to 2. Okay, now if we multiply the function by half, look at this one. Here is 0.5. If we multiply by 0.5, the value will be 4. The value remains same. Okay, the value will remain the same 4. But when? You can see here, it is 4 when x equal to 4. That means this time the value of x gets 2 times larger because the original function has half. You should see that. Okay, when the x values are double, the y values will remain the same. So for the same y value, the x values will be twice as large. So that is the meaning there. You can see this means the x values get twice as large for same y values. So that means if I want to make the table for the new function g of x, so table for g of x will be, okay, same table like before, x and g of x. Okay, 4 values there, 1, 2, 3, 4. Now look at this sentence one more time. The x values gets twice as large. So that means this 2 will be 4. That is the meaning, right? Twice as large. That 2 will be 4. 4 will be 8. 6 will be 12. And 8 will be 16. Okay? The x values get twice as large for same y values. The function values will remain the same. These values will remain the same. That is 1, 3, 7, and 11. 1, 3, 7, and 11. That is the meaning. So once you know the transformation, once you know the factor, it is easy for us to write these values. So one more time, just to recap what we have done. This is the equation given here. We see that there is a half. Half is a number between 0 and 1. And so once we know that this is the number between 0 and 1, we know that it is a horizontal stretch. And the stretch factor will be the reciprocal of this number. Here is a half. Reciprocal of half is a 2. That means the x values are increased by 2, keeping the y values same. So meaning of that is we double this x values and we keep the y values same. Okay, so once we know the core meaning of that factor, then we can easily construct the table for the transformed function g of x. Okay, if you have a question, you can ask me now. You can either unmute yourself and ask, or you can send your question through chat if you have any. Okay, look like there's no question. Let's find out whether we are done writing this down. Sagar, are you done copying it? Give me thumbs up. Yes, okay. Sandana? Okay then. Okay, awesome. So I hope you are getting in there. It's the factor that we are multiplying that x value plays a role in the horizontal stretch or horizontal compression. Okay, that's very, very important. Let's work on this one. I want you to copy the question first and try yourself. Let's see how much you can do. Okay, let's try this one. I'm going to give you maybe about 5 minutes. First, copy the question and solve it yourself. So screen share has stopped, right? Can you still see my screen? Okay, let me re-share it. I don't know why it has gone. Let's see. Give me a few seconds here when I'm trying. Something is not working. Maybe my internet connection. One more try. Let's see. It is still thinking. Okay, there we go. Can you see it now? Good. After you copy the question, make sure you try to solve it yourself. Okay. Okay, let's find out where we are at. Aditi, could you please unmute yourself and tell me whether you are able to solve it or not? You don't have to say the answer. Were you able to solve it, or you feel like you need help with this one?
I feel like I need help.
You need help? Okay. Let me check with few more beautiful people here. Let's see. Sagar, what do you think? Please unmute yourself. Sagar, please unmute yourself. Tell me whether you are able to solve it or you need help. You didn't find the unmute button? Okay, you're unmuted now. Yes.
And the transformation.
Say that again.
I think I'll need help.
You need help? Okay. Let me check one more. Let's find out. Diksha, what do you think? Do we need help with this? Yes. Okay. Okay then. Okay. Okay, everybody. Now look at the screen here. So the question says the transformation that changes the graph of the function f of x to g of x. So our original function is f of x. We are getting a new function g of x. Okay, f of x is the original function. F of x is the original function. And g of x is the transformed function. Okay, g of x is the transformed function. And if you look at the screen here, you can see that the shape of these two graphs are exactly the same. But this one, the original function is larger. Okay, and then the new function or transformed function look a little smaller. But what we can clearly see is the y values are exactly the same. So if you look at here, we have 4, here we have the y value 4, we have the y value same. But only thing is the x values are changing. That means we can clearly see that when we go from f of x to g of x, the graph is compressed, right? It's getting compressed there. And this compression is the horizontal compression. It is the horizontal compression. Okay, it is horizontal compression. So meaning of that is our equation should be like this. So for horizontal compression, new equation g of x would be f of b times, hold on. G of x is equal to f of b times x. This is how we write, right? And because this is compression, the value of b must be greater than 1, okay? And compression factor is 1/3. I mean, 1 over b, right? Compression factor is 1 over b. B must be greater than 1, and compression factor is 1 over b. What I mean by that, if you go back and look at your original slide here, if we have the compression, if we compress, b must be greater than 1, right? B must be greater than 1, and it is compressed by the factor 1 over b. So here, let's look at a couple of values. Okay, let's look at a couple of values. So you look at the screen now. Here you can see at x equal to 6. At x equal to 6, the value of the function, you can see for the original function, at x equal to 6, the value of the function is 4, right? And we have the same value. We have the same value at 2. If you look at 2 for the next function, at 2, we also have the 4. That means here you can see that if we multiply these 2 by 3, we get that 6, right? The value of b, then clearly the value of b is 3. Okay, you can also verify with one more point if you want. For example, you can take this point here where I'm pointing. That is the y value of 3 when x equal to 3. y value of 3 when x equal to 3. And here in the new graph, y value is 3 at x equal to 1. And you can see when you go from 1 to 3, it is also 3 times, right? So the graph is compressed, okay, by a factor of 1/3. 6 divided by 3 is a 2, or 3 divided by 3 is a 1. So the value of b must be greater than 1, so b is equal to 3. B is equal to 3. Okay, so b is equal to 3. So now our final answer will be, once we know this, we can say that this equation that we are writing here, this one, is now changed to g of x equal to f of b is 3x. Okay, g of x equal to f of 3x, as you can see. The reason is it is the compression by a factor of 1/3. Okay, the graph gets closer to the y-axis. That is a compression, and you can see that compression is a horizontal compression. If it is a horizontal compression, we multiply that x value. So here we multiply that x value by b. So that is the final result. Okay, so this is the last example for today. We are not yet done, but this is the last example for today. We are done with transformation. And today I'm not giving you any new homework or anything, okay? But next time we are going to begin a new chapter and you'll start seeing something new in this class, okay? So let me stop this live stream and we'll talk more after that.